So welcome to all our guests and all our Hebrew University friends. We have the pleasure to have Professor Retzker today for his lectures. I would like to remind you that our lecture will be around half an hour, and then we'll open the question and answer section. You can write your question to the chat, or you can raise your digital hand and we will open your microphones. The Nadia Gut-Biazini, the president of the Friends of the German-speaking Switzerland and governor of the Hebrew University, she prepared a short introduction to Professor Retzker because of their particular relation. So I will share with you now her video, and then we will begin the lecture. So here, okay. Hope you can see it. Can you see it? Yeah? Okay, so here.
Dear friends of the Hebrew University, on behalf of our friends of German-speaking Switzerland, I have the honor to introduce to you Prof. Alex Retzker and today's truly exceptional webinar with the title State-of-the-Art Quantum Computing. Alex Retzker is currently involved with the quantum computing project at Caltech in Pasadena, California, to which the company Amazon lately has attributed $500 billion. Prof. Retzker has been an associate professor at the Hebrew University since 2015, leading the Quantum Technology Theory Group at the Raka Institute of our university. The main focus of his research lies on theory. The theorist Alex Retzker has made fundamental contributions to the field of quantum technologies, mostly for quantum optics, quantum sensing, and quantum simulations. The theories are also pursued and elaborated in close collaboration with experimentalists. I also discovered an allusion to an area defined as laser pooling. In addition, Alex Retzker is developing at least one company in the area of his expertise, which is called Envision. In 2015, Prof. Retzker got awarded the Quill Prize. As 5 years ago at the Polytechnic in Zurich, on the occasion of the inauguration of a broader collaboration between Prof. Nadav Katz from the Hebrew University and Professor Andreas Wallraff from the Polytechnic, our association founded the Quantum Club. We have been following this specific exchange program quite a bit. Thank you, Professor Retzker, to help us understand a little bit more about quantum computing through your explanations. Moreover, we would like to get to know your expectations on how this technology may and will change our daily lives. Hopefully, after your webinar, we understand a little bit more about quantum computing than now. Professor Alex Retzker, we cannot wait to attend your presentation. Thank you very much.
Thank you, Nadia, even if she couldn't be with us today. And thank you, Professor Retzker. So I think the floor is yours now, and please.
Yeah, thank you for the invitation, and thank you for attending. Yes, I will give a presentation. So I'm currently I'm a professor at the Hebrew University. I'm also working on the Amazon project. Fortunately, I cannot say too much about the Amazon project. I will explain. I did make a few slides, but because it's an initial stage, yeah, so there are things that I cannot talk to about yet. But I will give you an overview of quantum computing where it stands. It's really fascinating time for this field. And I will talk a bit about the project in Amazon, and then we'll be happy to answer questions. Okay, so where do we stand with quantum computing today? Once in a while I give this presentation. Well, I gave it last time, like I think maybe 4 months ago, and I think since then things changed quite a bit. So it's really, this field is really changing very fast. There's lots of new results all the time. And I will give a brief overview so you will get the kind of the feeling what's going on in the field. Yeah, so what is a quantum computer? So if you think about a classical computer, so a classical computer is built out of bits. We can have 1 bit, it can have 0 or 1, and we can do 1 computation with this bit. We can have 2 bits, and it can be in all of these combinations of zeros and ones in 4 combinations, and we can do in principle, well, at each time we can have 4 results or maybe 4 components of computation in the computer. If we have 3 bits, we have 2 to the 3, and like this we have 2 to the n. And this is basically the memory of the computer, and we can do various calculations with it. What happens with a quantum computer? In a quantum computer, we can have not 0 or 1, but 0 and 1 at the same time. So it means that for 2 bits, we can have all of these combinations at the same time. And if we have a large computer with n bits, we have 2 to the n states, 2 to the n maybe computations at the same time. And this is the main intuition. This is a kind of a broad explanation of this intuition, very intuitive one. It's not really the case, and still for scientists, it's not actually clear if this is the case or not. But this is the motivation, that because of this, we can have exponential speed up, and we can do maybe exponentially large number of computations at the same time. Again, we know it's not exactly correct. We don't know where the border is, but there is at least one example in which people can show one useful example, and some maybe examples which right now are less useful. We do have an exponential speed up over a classical computer. And usually these quantum bits that can have both states at the same time, we usually like to designate them by a picture of an atom, because in many cases an atom is actually our quantum bit. It has, instead of 0 and 1, it can have up or down with spins, or ground and excited for the atom, and there is some kind of energy gap between them. But you can think about this picture as 2 states which are analogous to the 0 and 1 states of the classical computer. And like in the classical computer, also in quantum computers, we have to make an operation between the 0 and 1, but also between 2 different quantum bits. And this is the difficult task, how to do this. And in recent years, there have been lots of interest in this field, and the interest comes basically from industry. So up to a few years ago, it was an academic field. There was no activity, was extremely limited activity, maybe even none at all in industry. But in the last few years, suddenly industry and governments realized that there is a big potential in quantum computation. What I show you, here's a few slides to show this interest around the world. There was this Quantum Computing Act in the US Congress that decided to invest a lot in quantum computing in the US. And since then followed another few basic initiatives, one big initiative in Germany, one in general in the European Union initiative, and there's lots of initiatives also in China, lots of activity there. So just I will prepare a few slides, which I'll go over them really swiftly just to show what's going on in the world. All the big, basically corporates, well, most of the big corporates in the world are investing in this. There's lots of activity. Now, we'll start with China. I don't know much about this. In China, it's a bit less known, but Alibaba is working a lot on this. They have already providing a cloud computer of 11 qubits, and they have plans to enlarge it. And this is, Alibaba has the largest activity, but there's also Baidu, Huawei ZTE, which is more in telecom and communication, and Tencent is also in principle. They're more interested. They don't have, as far as I know, the hardware activity, but they're interested in quantum chemistry. There's also a very large activity in communication. So it is known that quantum communication is completely secure. And there's lots of activity around the world. I will not talk about this. It's quantum is so large that I can actually talk about all this. But here there's already, it's very advanced. So China has an activity to use satellites for this communication. And also in the West, there are ideas how to use satellite communication, how to basically use quantum communications via satellites. IBM has a very large activity, been there for a while, for almost 10 years, very successful. Google had very nice results over the last few years, and they basically demonstrated this, maybe the biggest result in the field of Google, when they demonstrated quantum supremacy, when they showed that it can do a computation that a classical computer just cannot do. Even though this computation was not important, it didn't solve any important problem, but still, it was a problem that they did solve a problem, maybe not important, but they did solve it, which a classical computer cannot solve at all in a reasonable amount of time. And in Microsoft, there's also lots of activities. They're going with something which is a bit much more risky, but they have also interesting activities in this field. Also Intel and Honeywell active in this. Honeywell has they just announced a small quantum computer which they built, which is a ion trap architecture. It's a very nice thing which they did. Still, they're a bit behind, I would say maybe Google and IBM, but they're closing the gap and have very nice results. And there's a lot of activities in startups there. So the big companies which I show you, they're active in this field, but there are, I think, around 100 startups already working in this field, and also have really impressive results as well. Okay, so I'll give a brief overview of the basically architectures, the main ideas how to build the quantum computer. The first one is built out of ions, and this is the first paper which showed how to do it. Well, they didn't demonstrate it, but they had the idea how to do it. And this is connected to trapped ions. People now know how to trap ions, and the story is very interesting because in quantum mechanics there is a problem. It's called the measurement problem. And in 52, Schrödinger, which was the most prominent scientist at the time, he said that, well, I quote, "It is fair to state that we are not experimenting with single particles anymore, that we can raise Lichysoteria in the zoo." This is kind of a fish from the dinosaur times. We are scrutinizing records, events long after that they have happened. And what he meant by that is, yeah, there's no point. So there's this fish, which I'm not sure if I pronouncing correctly, Lichysoteria, which we can study this fish, but there are a few questions which we cannot ask about this fish because it doesn't exist anymore, maybe about its metabolism or things like this. So there's no point, it's not a scientific question, there's no point discussing this. He said the same about operating with single atoms or single bits, quantum bits. There's no point in discussing this because we will never be able to do that. We will never be able to do this experiment. This was the most prominent scientist at the time, at 52. This just shows you what science is and how it's very difficult to anticipate. It was the smartest man at the time. And a year later, somebody says, actually, I know how to do that. Only a year later, and there was Wolfgang Paul, and he proposed how to make experiments with single atoms, and it's called the Paul trap. So he proposed it at 53. It took them some time, like 20 years, to build it, but he did. And eventually, now people can do experiments with single atoms. And this basically opened the field of quantum foundations and later on quantum computing. When you trap these ions, they form crystal. That's how it looks like. So it produces very nice pictures. And basically a crystal like this is a quantum computer. And that's how it looks like. These are the electrodes, they trap those. These are the ions. Each ion is a quantum bit. And these are being manipulated by lasers. And in the end, they are being measured with a CCD camera. That's a very nice story that shows how science evolves, how things which are to everyone looks completely unbelievable and unrealistic. A year later, they can become reality. And in trap ions, there's lots of activities. They have right now the best results, and well, in some respect, but in one respect, in this respect, is called the fidelity of a 2-qubit gate. It means when we are doing a gate, when doing an operation in this computer, there's always a chance for failure. And the very important number is that we have to pass the chance of a failure of 1 of 10 to the minus 4, which means we can only tolerate a failure if it's less than 1 operation in 10,000 times, we are more or less okay and we can build the quantum computer. Nobody reached this yet, but as you can see right now, the failure rate is 3 operations in 10,000. So we are very, very close to that. And once we're gonna reach this, once the people will reach this, then it will be much easier to build the quantum computer. Up to now, it was not reached, but you see for trapped ions, it's very, very close to it. And this number, by the way, so when I gave this talk, yeah, like 4 months ago, I think the number was different. It was I think 10 to the minus 3, and I had to change it yesterday because it already improved by a factor of 3. So field is really changing extremely fast. So there are many companies in this field for trapped ions, and these are maybe the most active ones, or the ones who have the best results. 2 startups. One is called IonQ, which came from the University of Maryland. Another startup from Innsbruck, from Austria, and Honeywell. And these 2 companies, they are more or less equal, and they have lots of activity, especially if you see those in the news when they want to go to the SPAC or the IPO in the stock market and basically be sold. They have a valuation of a few billions. And that's interesting because this field actually was mostly dominated by startup. The others are not, but now, okay, Honeywell is more or less at the same level. So maybe in the end, also this will go to big industry and not startups. And what they want to do shuttling. They have like small quantum computers with this number of ions. They're gonna move them, suppose to this area, make a gate, and then move them back. And like this, Honeywell, they have a small computer doing that already. So each of these companies, they have basically 10 years plan. And that's the plan of Honeywell. That's how the truck will look like. They want to reach 512 qubits by 2025. And then by 2030, they will reach a few thousand, maybe 10,000. This is the plan. The startup wants to use photonic interconnects. It means that each atom here will emit a photon, and the different atoms will communicate with photons, with light. So basically, they will not shuttle, they will not move, they will just communicate with each other. So basically, they will have like quantum communication from one to the other, and like this, they will make the operations. Like this, the quantum computer will be built. They also have very nice results, and this is their plan. They want to reach by 2028 10,024, but that's logical qubits. And each logical qubit is composed out of many qubits. And the reason for this is what I explained before, is that we need to reach this threshold, which is 1 error, less than 1 error in 10,000 operations. And the reason that we have to do that is because if we reach that, then basically we can reduce the error by an arbitrary amount and can have very, very precise operations. But then instead of having a single qubit, we need to have a lot of qubits. So if you have tens, maybe 100, that will encode 1 qubit. It's going to make many operations between those until we will be able to create effectively a qubit which does not have any error at all. And these are these logical qubits. And the last startup in this field is a European one from Innsbruck, from Austria. And they started a bit late, but they're doing very good work and they're closing the gap. And right now they have a machine on the cloud of 10 qubits. Okay, the other field, which is maybe the largest one right now, It's very interesting because it's not based out of ions, but just from electric circuits. So just by simple elements of electric circuits, exactly the ones that all technology or electronics is built out of them. And the idea was just to take a regular electric circuit to cool it down to very low temperatures. And once we will do that, then this electric circuit will start working in a quantum mechanical way. And in this way, it looks kind of simpler because we're using more or less the same electronics that regular electronics is working by. We're just cooling it down to very low temperatures. Once we do that, we will have a quantum computer. Again, it's a very simplistic explanation, but this is more or less the idea. And the advantage here is the scalability, because we know electronics is extremely advanced. And if you're going to use this, we can make large quantum computers. We don't have to invent the wheel, but just to use the same technology that we use today for modern electronics. And what some of you that remember this, or this is called an LC circuit. This is a capacitor and an inductor, and then the inductor is changed by a special inductor, which is called the junction, which is nonlinear inductor, and that's our qubit. And that's all. Just the basic electronic component. This is going to be the qubit. This is going to be the quantum bit with which we can work, and of course, this is a huge advantage. Yeah, it's not conceptually, it's not different at all than modern electronics. And that's how it looks like. Suppose this is one processor, and you see these are these lines, there are capacitors, and there are inductors, and basically sitting on a board. Again, very similar to regular electronics. So that's another, well, that's how this circuit, electronic circuit, looks like. That has basically 2 bits. And what happens here is that we can think about these electronic circuits, or we can think about this as these bits, as these quantum bits that can have 0 or 1. So when we take this electronic circuit and we cool it down, the same electronic circuit used for classical electronics, we just cool it down, it starts behaving quantum mechanically. So instead of looking at currents and charges, we can look at states, at quantum states. And when we bring them to specific points, they start exchanging information. And this is going to be the basic building block of this quantum computer. So again, a simple electronic circuit that we just cool down, starts behaving quantum mechanically, and then suddenly we can do computation. Okay, I don't have so much time, so I'll skip this slide. And in this field, IBM is a very, so they more or less were from one of the first, and they have very nice results. They can reach right now 6×10 to the -3. This is still order of magnitude worse than ions, but again, it's much easier to scale. These are just electronic circuits. And that's what people think, okay, right now they're worse than ions, but whenever they're going to improve just a bit, whenever they're going to reach this 10 to the -4, which may take maybe more than ions, then just modern electronics will build the quantum computer from that stage. They have also very nice results, and this is the plan. They want to go to 1 million qubits by 2030, and to reach and to improve these fidelities, so to reduce the error rate, the error probability, to go to this threshold which I discussed. There's also an interesting startup. So again, startups there's not so much in this field, but there's one startup that still has nice results called Rigetti Quantum Computing, and they also have their own fab, which they're very proud of. And another dominant player, maybe the most dominant one, is Google. Up to now, they have very nice results. They have more than 50 qubits, and also they have a plan by the end of the decade to reach around 1 million qubits. So, okay, there's another technology which is still everything starts with the atoms. The atoms, people thought that the atoms have no chance. They cannot compete with the ions. No, they can compete with the electronic circuits. But in recent years, suddenly there is improvement with the atoms. Again, that's the interesting thing with science. You can never know what in the end will work or not, or in which direction it goes. And the atoms are quite surprising. in the last few years, they have some disadvantages that people were basically pointing out to, but the biggest advantage is the scalability. You can bring many atoms. They are very small. You can bring them to one point, so you can, in principle, they are very compact, and it could be very simple to bring them all to one point and build the quantum computer. And the idea is the following: is they used what is called tweezers. These are basically lasers. Suppose in the picture here, it's a laser with a focused laser, and in the focal point there is when the laser is focused, then there is an atom. The atom is attracted to this point, and when it's attracted to this point, it sits here more or less in a steady way. And then when we bring them together, they can interact and form a quantum computer. And the nice thing that atoms are very small. The distances can go to below a micrometer, maybe half a micrometer. It can also be in 3 dimensions, which is very difficult with the other technologies. And in this way, it's possible to bring lots of quantum bits, lots of atoms to a confined region in space and to create a quantum computer. So here is this, if it can work, if this confinement with lasers can be so nice, then it's possible to build a quantum computer. But you see here is nice structures which they do. So each point here is an atom, and with the lasers, they're able to create this very nice configuration. So each point is where the laser has the largest amount of energy, and the atom is basically attracted to this point. And like this, they can create what they can write these structures or these structures. They can create very nice structures, and so nice 3D structures. And like this is possible. Maybe it will be possible to create a quantum computer. And the idea, how does it work? If we bring 2 quantum bits together, so we can operate with 1 bit and just bring it from 0 to 1. So make this quantum operation, which is completely analogous to the classical one. Also in the classical, we go from 0 to 1. Also here we go from this state to this state. But if the atoms are very close together, and if this atom is in this state, it doesn't allow the other atom to make the operation. And that's a physical effect that's called Coulomb blockade. It's because the physical interaction between the atoms, and this physical interaction, that's what allows to make the basic building block of a quantum computer, is that when this atom is in this state and is close to the other atom, then the other atom cannot make this operation, and this is the case. So it's a very simple, very compact structure. And at the beginning, it didn't work. So a few years ago, the fidelities, which is the rate of failure, was very large. But in recent years, it went, the rate of failure became very small, and now it's already 5 10 to the -3, so very close. So already at the level of the circuits and very close to the ions. It's a very surprising field. Well, surprising in the way it basically had success in the last few years. It's very interesting. Would be very interesting to see where it will go to. And right now they have already processors of hundreds of atoms. It's not exactly quantum computers, but they are getting them. Okay, I will skip this part. Okay, so now I will give a short introduction to. Okay, so what we are doing at the Hebrew University, and then we'll discuss a bit about. 1 minute. Yeah, we'll give a short introduction to what we are doing at the Hebrew University, and then I will discuss a bit about what I'm doing at the project in Amazon. So at the Hebrew University, we have a large quantum center. It was one of the first ones in Israel. And we have already 21 researchers working in this field of quantum physics. Again, quantum information is not only quantum computing. It's actually, there are many ideas. There's quantum sensing, there's quantum communication, and there's quantum simulations. Some of those, especially quantum sensing, are already going to industry, also quantum communication. it's just that quantum computing is basically has maybe the largest, it's a very high risk, high gain field, and maybe has the largest prospect in the future. But right now, the other fields, they're already at the technological level. So we have lots of activities, a partial list of the activities we hear. What you see, it's really in many fields. It's there's theory activity, and I'm doing theory. There's also lots of activities in quantum defects in solids, in atoms, in lots of in superconducting devices. Dov Katz has been running a group for a long time here, does superconducting devices with the goal of quantum computing, and lots of many other fields which are connected to biology, to biosystems, and also more exotic quantum features like topological states. There's also a company that was created in the Hebrew University by Hagai Eisenberg. It's called QuantLR, which deals with quantum communication. Again, this is a field which I will not discuss, but it's a very advanced field. It's already a viable technology. In some countries, people already can use it for communication, for secure communication. And they are in China, they are working, but also in the West, how to basically use quantum communication in satellites, that every point on Earth can be connected to every other point, can have this secure quantum communication. That's what I'm doing, been doing before. I've done quantum computing, I've been working in quantum sensing, also a startup company which is called Envision. And this is, and the nice thing is they can use, and this has a very large prospect for the future. I believe it's very much optimistic about this field, that you can use quantum technology for medicine, and I believe there's going to be a huge impact on medicine by quantum technologies. But also we have other things like interferometry, quantum error correction, and very good photon detectors. Okay, so now just explain a bit about what I'm doing. Okay. Okay, so I've been doing before. Again, I cannot talk too much about Amazon. I'll explain the main idea. I've been doing before theory for quantum computing. And the things that I've been mostly fascinated by is precision. Precision of measurements, which in the end, it's connected to precision of operations. And this is the nice thing and the very, maybe not so trivial connection, but technically it's not only connected, but it's more or less the same. Because quantum computers require such a huge precision, so we can only one operation out of 10,000 can fail, and the probability to fail is very large, because we'll discuss it a bit. Unlike a classical bit, which can have only 0 and 1, a quantum bit can have 0 and 1 at the same time, but also in lots of configurations. So it's very hard to prevent an error, and the error rate should be extremely small. So precision is maybe the key thing in quantum. And that's very important for gates. And this is a partial list of gates that are designed and been created, realized in various labs in the world with a very high fidelity. But I also took these ideas for precision measurement. So I thought, okay, if we can do things so precisely for quantum computing, maybe we can turn this problem around and can use this precision to measure things. And that's, of course, measurement, detectors, sensors are very important. And here is a list of results of ideas that I had, how to measure things very precisely, that again been realized in various labs, in various institutions in the world with, at the time, state-of-the-art precision. And then I thought maybe we can apply it to medicine, maybe we can apply it to NMR or MRI. So this is a typical MRI machine, and that's a typical NMR machine. And an MRI machine in the end gives us a picture, which is divided to voxels. And the size of each voxel is on the order of 10 to the 13 spins. And the idea is to increase precision to this amount, then the size of each voxel is going to be just a single spin, to get a picture at the precision of a single atom. And there are many ideas to do this. One of them is based on the field of NV centers in diamond, is to take a diamond and find NV or a few NVs next to the centers. NVs are special molecules that are created naturally, or we can also do them artificially, but are created naturally in diamond. And these atoms, and the interesting things in these molecules, or small molecules or large atoms, depends how we look at it, but they actually quantum bits. And because of this, they can be used for very precise measurements. And then we can put even a single molecule on top of this, and they can measure this molecule, characterize, find the structure, find many things about it that we're interested for scientific or technological pharmaceutical reasons. So we can also do this, suppose with a blood test or whatever test that we want to do, and get an extremely precise result down to the level of a single cell or a single molecule. And this is one of the first results that was ready in 2012. Since then, it improved a lot. But what you see here, it's a measurement. This is an NV center, and it can measure the structure of the in-room temperature, the structure of the diamond. And what you see here, these are the various, it can actually talk to every carbon in the diamond. What you see here, this time we didn't know that we were talking to one of those. It was measuring one of those. Since then, the measurement was improved. Okay, so I don't have much time, so I will skip this part and I will go to Amazon. So yeah, basically in a few months ago, I joined this Amazon endeavor to build a quantum computer. So basically, it's a competing project to all the projects that I showed you. And it's a big project that was right now is centered in Caltech, in Pasadena, and I've been asked to join. My group and myself were asked to join to this project to do theory for the project. And right now I'm here in California, and my group at the Hebrew University collaborates very strongly with this project and with Amazon. And the idea in Amazon is to also use acoustic cavities, to use acoustics. And the idea behind acoustics is because it can be very small and have very long coherence time. So what it means when we look at acoustics waves, these waves, they oscillate for a very long time without using the shape or the form. And we can use this as a basic qubit. Again, I cannot go into the details. I just explained the main idea. And the main idea is the following. Oops. Yeah. So if we think about classical correction, so also classically, if we have a classical bit that can have 0 and 1, there can be an error. So what we are doing, in order to correct this error, we are doing the following thing. Suppose instead of 0, we're using 3 bits, 0, 0, 0. And instead of 1, we're using 3 bits, suppose 1, 1, 1. And we're starting the computation. Also classically, it is done in many classical computers. So instead of 1, we're going to have 3 ones. And if there is an error, suppose this one flips to a 0, we can just do a majority vote. So there are more 1s here than a 0, so we're going to correct the 0. And we're going to bring it back to 1, 1, 1. And this is the main idea. And again, a bit simplistic, but it's the main idea in error correction. That's how we correct error in classical computing. But if there are 2 errors, then we cannot correct. But still, a single error like this will be able to correct. What is the problem with quantum computers? The problem is that we cannot do the same thing. So in quantum computers, we can have 0 and 1 at the same time. And because it's in the same time, so I mean, suppose we have a classical bit, can have either 0 or 1, and there is some probability that it will change from 0 to 1. But the quantum computer, the quantum bit, because it's 0 and 1 at the same time, it can be in various probabilities at the same time, not only probabilities, also what we call phases. So it's not only 0 and 1, it's 0 and 1 at the same time with various numbers with various probabilities. So it's very difficult to correct because we're not correcting from 0 to 1, we are correcting from some number here, the speed that can be 0.52, and an error would be, instead of 0.52, it becomes 0.51, and we have to bring it back to 0 to 52. So it's very, very difficult to do. And in recent years, there have been ideas how to convert this very complicated quantum bit to this very simple classical bit, but still to do the quantum computation. I will not get into that, but this is the main idea, somehow to use actually classical computing ideas for quantum computing to make it very simple, but still have the advantages of the quantum computer. And basically this is what Amazon is pursuing. And with this, I will thank you for your attention. Okay.
Sorry, here I am. So thank you a lot, Professor Retzker, for the interesting lecture. We have already few questions that I will read for you, and I would like to remind you that you can also raise your digital hand. So let's, we have a question from Stephen Franklin. What difference does it make which type of atoms are used and which elements atoms are mainly used in quantum computing?
Okay, the difference is not conceptual. It's the same conceptually, mathematically is the same thing. In the end, we have a quantum computer and it has bits, has quantum bits in some state. And in the end, indeed, this is exactly the same. But for technological reasons, for realization, there is a huge difference. It's a completely different technology. It's a completely different infrastructure. And the question, the big question right now, what is easier and what is most realistic, in which field should we invest right now to build a real quantum computer in 10 years? This is the biggest question. And here the difference is basically, it's huge. This is the difference between failure and success. And so technologically, it's a very, very big difference. It's almost, I mean, I've been working as a theorist. I have the advantage that I can work in many fields. I can work in ions, now I'm working in superconducting. Before I worked in NVs, almost work in all of those. Again, mathematically, and what I'm doing is very similar, but the physics behind this is completely different. There is almost no connection.
Okay. Another question is more practical. Could you please give some practical application of this research? What will this allow to do that we cannot do it today and with today's supercomputers?
Okay, so that's a very good question, and the answer is not so clear, to be honest. There was one thing, and the biggest thing, that there was it's called the Shor algorithm, and it's basically how to break codes. So in a way, and this we know it can do very well, it can break codes, but it's in a way, it's kind of we know that the quantum computer can do lots of damage, but what can it do actually, which is very good. But this ability to break codes, which is exponentially faster, much faster than a classical computer, that give people the understanding that probably there are many other things. And there's lots of theorists working on this to find other things. So what do we do? Okay, so, but before I answer this, mainly theorists been looking for ideas that have what is called exponential speedup, that it's exponentially better than a classical one. That is a huge advantage. And when people think about this advantage, they're always considering this exponential speedup. A smaller speedup we know is doable in many other areas, but we're still looking for this exponential one. And now there are many algorithms that go towards, well, physics and chemistry. And the reason is that we know that nature is quantum mechanical, that we know. And so if you want to simulate nature, there should be a huge advantage in using a quantum computer, because right now when we're simulating quantum process, we're using a classical one. But what are the quantum, because nature is quantum mechanical, we know that at large scales, it is behaving in a classical way. That's why classical mechanics is very good in explaining or forecasting experiments, experimental results. But in quantum chemistry, we know that actually quantum mechanics will play the role, and that's why most people are looking in this direction. And this is mostly for material science. You know, for material science, if you want to create new materials, it's very difficult to use theory for this. We have to try this and try that until something works. Theory is very difficult, again, because in the end it's quantum. And for this, we believe quantum computers will be very important, and this will have implication in the pharma industry and probably in the computation industry for fabs. But there are also other things which people are less looking, and most of the theories are focused in this direction. But basically, it's very hard to know what the quantum computer will be good for. But the main intuition is because the world is quantum, so at nanoscales, everything is quantum. So we believe in the nanoscales, the quantum computer will be very important.
Okay. Here another question. What can you say about creating encryption scams? Sorry, I just missed it. Encryption schemes that would be resistant to quantum attack, to QC attack, sorry.
Yeah, okay, so okay, so first, I'm not an expert in this. This is really cryptography. I think the experts in this are actually people who are doing classical cryptography. I mean, this question can be, one is how to use quantum computers for this, and this is easy. The other one is the classical thing. And there's, again, I'm not an expert in classical cryptography, but now it's a very active field. And now there's huge activity to find something which will basically will be used instead of RSA, which be protected against quantum computers. I don't know. I think people are optimistic, but again, it's very hard to know if you will be protected against it or not. I mean, also for RSA, it took a lot of time, but basically. But I would say I'm not an expert in this. It's a very active field, and there's lots of people who are optimistic in this direction as well. There are other people that believe that it's not the right way, and that the quantum computer can actually break many codes, not only RSA.
Okay. Do you see any future application for quantum computing in fuzzy logic and non-binary systems?
Okay, so that's yes. So the point is that it's very hard to know until you see results. There are some people who are looking in this direction. I don't know. There's no conclusive answer to this. I don't know.
Okay, that's a nice answer too. And I think just let me check. Okay, if you want to learn more about quantum computing, would it be better to focus your study on computer science and engineering, or the quantum mechanics experimental physics side? I think our friend is at the beginning, maybe. So
just to learn. So the first ideas, many of the ideas in quantum computing came from computer science. So, but I would say, and computer science has had a huge impact on this field. But I would say if you just want to learn, so it's possible to learn these results without knowing so much. You have to know some basic things about computer science, but you can understand those without knowing so much about computer science. If you want to work actively, then you have to understand computer science very well. But just to understand how it works, I think you don't need to know so much about computer science. So I would say maybe the physics is more important. Maybe understanding quantum mechanics is more important.
Okay, so whoever this question, it was an anonymous question, maybe we'll see in the Hebrew University in the next years. So I think this was the last question. If you have any more question, this is the time you can ask.
There's one question I think about, do you have a feeling as to which approach might have a more successful results in development of AI technology? Okay, so AI, that's it's an interesting point. So AI recently also has a lot of impact in for quantum, for two directions. One is to use AI to develop the quantum computer. That was very successful. Basically, error and probabilities are important in the build of a quantum, in this effort to build a quantum computer. And the machine learning was always a very good thing for this, and this does help a lot. But also to use machine learning on a quantum computer. Again, there's not definite results, but there's lots of indications that indeed you can do that, and that's going to be extremely beneficial for AI. Again, it's not there's no definite results. Some people would say that it's not true, but there are more and more people who are claiming that they see this numerically when they check it, and some theoretical results as well, analytical ones. So indeed, lots of people believe that AI can work on a quantum platform and will be extremely impactful.
Thank you a lot, Professor Retzker. So let's see, we just received another question. Okay, what's the roadmap of future developments and collaborations in the Hebrew University, whether with the academy or in the industry?
For quantum computing? Right now the collaboration which I have with Amazon, it's a long-term collaboration, probably will continue maybe till the end of the decade. So that's a very important collaboration, but there's lots of people at the Quantum Center that are looking to open startups. And again, because there are these big corporates, Amazon is one of them, that choose a direction. Usually when a big corporate chooses a direction, it's a very large ship that goes in one direction, cannot change its course. And as you see in science, it's very difficult to know. Maybe in the end, all of these ideas are the wrong ones, and there's another idea, a much simpler one that will make the quantum computer work much better. It's definitely could happen, and I showed you this example with Schrödinger when it said something is completely undoable, there's no chance, and just a year later, somebody came up with the idea. And because of this, that's how I feel there are many startups that taking different directions, and they say, okay, if we'll be successful, if we're not successful, but if we are, then we can be much more successful than all these big corporates investing billions in their effort. And one example is this atomic one that nobody believed in it, but now suddenly they have very good results. So lots of people are basically looking in these directions, and they want to open startups. They have various ideas, but also in like superconducting, there are people having ideas which are different than what the big corporates are looking at. So I do believe that many people at the Hebrew University, many researchers will open startups in the next few years. Yeah, but we'll have to see exactly.
We will wait and see. And as we know in the Hebrew University, there are a lot of good ideas. So I'm sure some good ideas will come from us. So I think this was the last question. I would like to thank you and to wish you good luck there with Amazon and far away from us. Hopefully to see you soon here at the Hebrew University, but if not, again with Zoom. And to all our friends, this lecture has been recorded, so I will send you in the next days. And if you have any other question or anything you would like to tell us, please contact me or write me a mail, and I will forward it to Professor Retzker. So thank you, everybody. Thank you, and enjoy your day or your evening.
Thank you.